Hello, hello, beautiful people. Welcome to 1.3 and 1.4 in a little bit. Real numbers and the number line. Today's SWABAT is to classify, graph, and compare real numbers and find and estimate square roots. So some vocabulary as we normally do. Radical. This is a radical. There's my square root symbol and the number inside of it is my radicand. Radicand. The other thing I want you to really know and study and memorize are perfect squares. Now, instead of just giving the list, I'm telling you where they came from. The first perfect square comes from 1 squared, 1. So the perfect square here is 1. The next perfect square comes from 2 squared, which is 4. The next one, the next perfect square is 9, because 3 squared is 9. 4 squared is 16. 5 squared, 25. This is how I generate 7 squared, my list of perfect squares. So 7. 8 squared is 64, 9 squared, 81, 10 squared, 100. Write these down. 11 squared, 121, 12 squared, 144, 169 is 13 squared. And then the only reason why I remember what 14 squared is because I just switched the 6 and the 9. It's 196. It's the only one it works for. Comma, dot, dot, dot. There's an infinite number of those, but those are some of the more common ones that I really want you to memorize. Okay, the next thing I want you to know about is a set. So a set is a well-defined collection of objects. You are part of a set. As a student at Notre Dame, let's say that is my set. Set is Notre Dame students. Each object is called an element. So what are the elements in the set that I just gave you? Well, those would be the Notre Dame students. So that might be Bev, it might be Jenny, it might be Tanisha, it might be Maya, it might be Susie, it might be all these different names. Those are the objects in my set, every single Notre Dame student. A subset of that would be the freshman class, for example. That would be a subset because it's a group taken from the larger group. If I remixed it, and let's say instead I wanted to say that my set is all of my Algebra 1 students. The elements are my students that are in Algebra 1. And then my subsets might be Block 1 or Block 5 or Block 6 or Block 2. Those would be my subsets. Okay, types of numbers. Rational numbers. Rational numbers is any number that can be written as a ratio, rational, see it's in there, R-I-T-I-O, ratio, of 2 integers, A over B. A number with a decimal, it's also known as a number with a decimal that either repeats like 1/3 is it as a ratio, but that's equal to 0.333333, and it goes on forever. That's how we would enumerate that. Or it terminates like 1/2 is written as 0.5, period. It ends there. There's no more to it. Now there's natural numbers, also known as counting numbers. We don't use these as much, but it's 1, 2, 3, 4, 5, 6. It's like when you're a kid and you ask, or if you have a kid and you don't have any kids yet, let's be clear. If you ask a kid to start counting, they're going to start with 1 typically. Those are the natural numbers. Whole numbers are almost the same thing, except they include 0. So natural numbers would be a subset of whole numbers because it's part of a bigger picture. And then integers are the same thing as whole numbers, like if you look at it from here to here, but they also include the negatives as well. So I would say positive and negative whole numbers. What we like about them is there's no positive, no negatives. I'm sorry, there's no fractions and no decimals in integers. One thing to note, rational numbers, these can be positive or negative. No one cares, but you can be fractions, decimals, or not. Integers, or I'm sorry, irrational numbers. That's a number that can be written as the quotient of 2 integers. That cannot be. Let's underline that because I just messed that up. Their decimals do not repeat and they do not terminate. They go on forever and ever and ever and ever and ever. Without any rhyme or reason. So there's no pattern to it. You can't just be like, oh, guess what? I think the next number is going to be 5. No, it's 7. They just go on forever. You can't really rationalize why. While we're at this, what I gave you a picture of is a group of rational numbers and irrational numbers. Collectively, they're all real numbers. That's the one thing they have in common. They're all real numbers. 2 subsets, rational, irrational. I want to start with irrational numbers because we were just now talking about them. Don't terminate, don't repeat. The most popular one in the whole wide world is pi. It's about 3.14, but if you enter it in your calculator, it goes on forever and ever and ever. Now, the other thing that's popular, well, not really popular because no one really talks about it, but the other way to get irrational numbers would be like the square root of 5, square root of 20, square root of 19, square root of 3. Does it have to be an odd number? No. Square root of 44. However, the main thing here is it's the square root of anything that's not on my list of perfect square. Any number that's not a perfect square that you're taking the square root of is irrational. I promise. What else would you like to know? Well, let's talk about the rational number side of this. We have 3 different groups that we're mostly going to be looking at here. The first one is whole numbers, which we know is 0, 1, 2, 3, ... 17 is a whole number, 99, so on and so on. Integers are all of this. The integers include all of these whole numbers plus the negatives of them, like -2, -3. It still has whatever positive number you can think of, 77, but it also has the negatives as well. Now, rational numbers has all of that. It includes everything that we've written down here. So you have your positive numbers like 39 and 22. Then you have your negative numbers, -45, -17. All of that. But it also now includes your fractions, your 1/2, because it terminates. It includes your 1/3. It includes your -2/3. It includes your decimals, 0.45. It includes all of that, as long as it terminates or repeats. So let me go ahead and write, let's say it was 0.5 repeating. Okay, that's the universe of numbers that we'll be dealing with in this class. Now let's simplify, and when I say simplify for these, I basically want to know what number times itself gives you 121. It's 11. But if you forget and you're like, I don't remember, then you can go back up here and you can just kind of number all these: 8, 9, 10, 11, 12, 13, 14, and you know, okay, 121, 11. Now, I'm not afraid of fractions. I hope that you're not either. I'm going to break this down into the square root of 64 over the square root of 9, which would be 8. Square root of 64 is 8. Square root of 9, what times itself gives me 9? 3. Improper fractions, I'm cool with. They're fine until we have to graph. Then we might need to switch them up just to make our lives easier. Am I afraid of decimals? No. I know that the square root is not a lot that I'm afraid of, but ants, I'm afraid of ants. 0.81. So square root of 81 is 9, but what about that decimal point? Well, I'll tell you, there's 2 numbers after the decimal point, so I'm going to cut it in half. So I'm going to move the decimal point over 1 time. And then, sorry about that, move the decimal point over 1 time. So my answer is 0.9. How does that work? Let me show you again. Let's say I have 0.0025. Well, what's the square root of 25? 5, you might say. And then I look at this. There's 1, 2, 3, 4 places, right? 1, 2, 3, 4. Cut them in half. This seems aggressive. So now I should have 1, 2 numbers after the decimal point. So my answer is 0.05. Like it? I love it. Get at my level. Okay, next thing I would like to do is some estimation, because at the end of the day, we don't always have perfect squares, number one, And then number 2, sometimes we just want to estimate about, what is it? So that's what we want to do for this next example. Estimate the square root, round to the nearest integer. All right, well, I have radical 15. Which two perfect squares is 15 between? Not between 1 and 4, not between 4 and 9, but it is between 9 and 16. So it's close to 9 and 16. Then you ask yourself, which one is it closest to? It is closest to the 16. So that would tell me that square root of 15 is close to whatever the square root of 16 is. The square root of 16 is 4. So this is closest to 4. Same thing for 50. I know the lettering is off. This should be a B. What is 50 between 49, it looks like, is the lower part of it. Can't really get closer than that, huh? Or 64. I think it's closest to this one, and I'm right. And what is the square root of 49? 7. So the nearest integer that is to is 7. Okay, find the approximate side length of the square figure to the nearest whole unit. Nearest whole unit makes me feel like I'm going to be doing kind of the same thing. So this is a square. We know that the area is equal to the side squared. And I want to know, well, what's the side? And if I want to find just the side, that means I just want to know what the square root is about. So that square root 60 is between which two numbers? It's between 49 and 64. Then you ask yourself, which one is it closest to? 64. So this is about 8, but about 8 what? I do love units, and they did give me feet squared, so I would just be left with feet for my side length. You like it? I love it. All right, this is a longer lesson, and thank you guys for sticking with me here. 1.3, almost done. Name the subset or subsets of the real numbers of which each number belongs. So the main ones that we're going to be using for this when we do this are rational, integer, whole, and maybe it could be irrational. I'm pretty much going to work my way from top to bottom. So the first thing, oh, buzzkill, you can see my nails jacked. The first one here, rational. Is this a rational number? Yeah, it's a ratio of two integers. So I'm going to say yes on that one because it's a fraction. Is it an integer now? Well, no, because integers are positive and negative whole numbers. So not an integer and not also a whole number. I'm working my way from rational numbers, integers, wholes. Automatically, though, if it's not rational, I'm just going to say irrational and then be done with it. Part B, is that rational? -5, yeah, it terminates. There's no decimal point after it, so it is rational. You can say rat if you want. Is it an integer? Yeah, it's a positive or negative whole number. It's actually a negative whole number. There's no fraction, no decimal. Is it a whole number? No. Why? Because it's negative. So I'm going to stop right there. Pi. Is pi rational? No, it goes on forever and ever and ever with its decimal. So I'm going to go ahead and say irrational. And as soon as it's irrational, I can stop there because there aren't any subsets in irrationals. All right, go ahead if you want to. You can press pause and try this one by yourself, or join me here in saying it's rational and it's an integer because it's whole and it's whole. Integers, just note though, integers can be positive or negative. No one cares. If it's a whole number, it's automatically this and this though. Kind of cool. Okay, beautiful, beautiful people. I would like to compare the numbers, and when I compare, I'm using either less than points to the left, and greater than points to the right. When I'm comparing, I'm going to always point to the smaller number. Always point, so this is the point, to the smaller number. Always. Well, 4/5, if I was using a calculator, I would divide 4 by 5, and I would know that's about 0.8. And then 1.3 is about 1 point, I don't remember, but I would look it up on a calculator though, and that would tell me that 1.3 is about 1.14. About. Which one of these is smaller? This one is smaller. So I'm going to say 4/5 is less than 1.14. Now pi is 3.14 about. You know it goes on forever, but that's about what it is. 19/6, if I were to divide that on a calculator, I'd get 3.16, if you could believe me. You can believe me. And so if I didn't have a calculator, what would I do? I would divide 19 by 6, just using long division, and get 3. 18. And then I would just kind of keep going on there. And I would add zeros until I knew, because right now 3.1, that doesn't tell me much. But I do know that 6 goes into there 6 times, because that's 36. So this is about 316. John 3:16. Which means that this one is smaller, so I'm going to point my arrow to that one. So pi is less than 19/6. I don't know exactly what pi is, but I do know that it's less than 19/6. All right, next thing, press pause and order these numbers. Simplify them first if you'd like to, but put them in order from smallest to biggest, please. Okay, so hopefully you paused, and if you did, you should get the smallest is -1 square root 121, because it's a negative number. Those are always smaller than the positive ones. 2/3, 1.875, radical 64, radical 95. I'm going to tell you, real talk, I did mess up because I forgot that this was negative and I was going to put at the end there. That's why I have that comma. And it's also why this radical is way, way out there. Now, typically, I try to make your videos about 15, 16 minutes or so. This one's a little bit longer, so if you need to, do me a favor, go ahead and either press pause or something before we get to the backside. The backside won't take as long, but I did want to give you a minute to take pause to digest some of what we did. If not, or if you're ready right now, or if you pause and now you're back, welcome back. I'm glad to see you. We are doing 1.4 properties of real numbers. What's my swab at? Well, I would like for us to be able to identify and use properties of real numbers by the end of this. So first thing I want you to know is equivalent fractions. Equivalent fractions. Well, what is that, Ms. Fitzgerald? Nothing that we're talking about. Equivalent expressions, though, we have. Equivalent fractions was like 1/2 and 2/4. Same thing with expressions. They both will simplify to the same thing. Now, some properties you've probably seen before. The commutative property. And this happens with addition and multiplication. Changing the order does not change the sum or product. So A plus B is equal to B plus A, and A times B is equal to B times A. The sum or the product doesn't change the order. It doesn't change the result, regardless if you change the order or not. Associative property, changing grouping symbols, for us, going to be parentheses, does not change the sum or the product. Oh, my bad. But what I do want you to notice, though, kind of important, is this is still A, B, C. A, B, C. I'm only changing the grouping. I'm not changing, because right now A was with B, now B is linked together with C. I'm not changing the order. Please, please, please notice that. You don't change the order, just the grouping. Cool. Identity property, there's two types. One for addition, so adding 0. So identity means I should be able to keep my 0. Keep my, spoiler alert, keep my identity. So what could I add to A in order to stay A? 0. What could I multiply by A in order to keep my identity as A? 1. Multiplying by 1 and adding 0 will not change the result. Now, don't get this confused because this is separate. The zero property of multiplication. That tells me I should be multiplying something and 0. So if I multiply any number times 0, I should get 0. Multiplication property of -1. The product of a number and -1 is its opposite. So if I do a times -1, I should get -a. Okay, looking at those 1, 2, 3, 4, 5 properties, name these properties for A, B, C, and D. I do legit want you to press pause right now. Name the properties for A, B, C, and D. Okie dokie. So for the first one, commutative property of multiplication, because all we did was switch the order here and here. Part B, multiplication property of -1. Some people will see parentheses and automatically go with associative property. Not you guys, don't fall for it. All I did was change from here to here, so that's there. And then for C and D, they're kind of the same. Identity property, because I started with M, ended with N. But for C, it's identity property of addition. For D, I started with 53.7 and I ended with 53.7. So that's the identity property of multiplication. Okay, my next step, beautiful people, is to simplify each expression and justify each step. So I want to simplify. These are grouped together, but I cannot combine them because this has an x and this one does not. So I do want to add 6 and 12 together, and I'll deal with that 8x later on. 6 and 12, well, what did I do? How is that legal? Well, basically, I just moved this over here. I moved it. I commuted it. So it is the commutative property of what? Addition, because I'm adding. And then I can add 6 plus 12 is 18. And that 8x will stay there. And for that, all I did was simplify. I didn't use a property for that, just arithmetic. Okay, part B. I can't really multiply 16 times P, but I can multiply 16 and 5. And what makes it so that I can do that instead of multiplying these two, that is the associative property. I didn't switch the order of multiplication. And then what do I get? 80. How did I get it? I just simplified. That's all. I do want you to really kind of start justifying, just because I think it'll be helpful when you start thinking about geometry for next year and whatnot. Let's start early. Now, tell whether the expressions in each pair are equivalent. Well, let's see. Let's do a little simplification here. What's 4 plus 6 is 10 plus x on the left side. And is that equivalent to, well, what's 4 times 6 looks like a negative 4x? Nope. So no, those are not equivalent. They're not the same. Well, let's look at this one. Left side, 4 minus 4 is 0. So that's 0, because p times 0 is 0. Is that equal to 0? Yes, that is equivalent. Left side, 12 minus 7, order of operations, is 5 plus x. There is no way that that is equivalent to 5x, because one's plus and one's multiplying. So I'm going to say no. Get a lot in this lesson, beautiful people. Take a moment and look back and write down something that you learned or that you saw differently today than what you've seen before. That's what I would like for you to write right here. Thank you so much for joining me, and have a delightful day.